All right, three-phase circuits. Those of you who work in power systems, there is no way you can escape three-phase systems. There is no way you can escape three-phase circuits. There is no possibility of you not coming across Y configuration, delta configuration, square root 3, and 30 degrees. Okay. Now, interestingly, this is my observation. Okay. I'm not generalizing, but this is what I've observed. Even folks who are working in the industry, power systems engineers who are gainfully employed, okay, tend to be a little bit wishy-washy with respect to square root 3 and 30 degrees. Where is square root 3 and 30 degrees coming from? What is our origination? When do we have to divide by square root 3? When does the 30-degree phase angle get added to which quantity? When it gets subtracted from which parameter from which quantity? I recommend my students enroll in my FE electrical program in the PE power program to go through a detailed step-by-step derivation, which we are going to do shortly for the delta network, at least once. It is extremely important. In fact, in my FE electrical and computer exam preparation program, I go through this once with both Y network as well as delta network. And then in my P power program, I go through it again in a lot of detail for the Y network and delta network. And once you go through it in a stepwise manner, the entire mystery about when should I multiply by square root 3? When should I divide by square root 3? When should I add 30 degrees? When should I subtract 30 degrees? It will completely disappear. Okay, but you have to take time and go through all the steps. In fact, as you're going to see, you have to have the calculator on you and do the hand calculations for the derivation at least once. If you skip this step and tell yourself that, I'm going to memorize these, no need to derive it. We live in the day of ChatGPT and Google. Every answer is out there. You just have to ask the right question. Sure, but in the moment, if you're doing commissioning, if you're doing startup, if you are in a meeting, if you are troubleshooting, will you be able to sort of connect the dots and cross-reference and come up with a solution? Highly unlikely. Okay, so let's go through this in a stepwise manner. So the three-phase circuits, by and large, you encounter two configurations. You have Y configuration and you have a delta configuration. There are other configurations, zigzag, Scott-T transformer, things like that, but you would rarely encounter them. So let us assume that about 95, 98% of the configurations, especially in terms of transmission, distribution, and generation, right? What you encounter are either Y configurations and delta configuration. Now, with the Y configuration and delta configuration, now you have four possibilities. You can have a source that is Y connected and a load that is Y connected. So this becomes a Y configuration. You can have a source that is Y connected. You can have a load that is delta connected and becomes a Y delta, similarly delta Y, and similarly delta delta. So these are the four configurations. In some way, shape, or form, they can be thrown at you. If you pretend to know three-phase circuit analysis, you have to be comfortable tackling them head on. Okay, so your source connections and your load connections. Now, there are some unspoken rules around representation. There are some unspoken rules around how you must interpret and communicate whether the given parameters and quantities, and for the most part, when we say parameters, we are talking either about voltage or about current, because if you know voltage and current, you can figure out reactive power, real power, complex power, apparent power, impedance, anything that you want, right? So the unspoken rule, as far as notation is concerned, which you're not going to find explicitly given in the FE electrical reference handbook or the P power reference handbook, and I would even dare to say that in most of the textbooks, okay, is that the subscripts, if the subscripts are small letters, it actually indicates sources, okay? So what we see on the left-hand side is a Y-connected source, okay? VA represents phase A to neutral, phase A to ground, phase A voltage on the source side. So this is basically a generator, a Y-connected generator. Okay. This is basically a generator, a delta connected generator. Why? Because you have the subscripts, small subscripts, okay, small letters. So this is an unspoken rule. Now, if I really want to test you thoroughly and keep this in my back pocket as a knowledge piece, right, which you are able to and figure out whether you're able to understand this or not, I may not even explicitly tell you that the voltage, let's say line to line voltage that I'm providing you in the problem statement, whether it is on the source side or on the load side. But there is a way to sort of make inroads into that particular problem, create a dent. How? By understanding this concept that if the subscripts are small letters, okay, then that is the source. Okay. If they are capital letters, which we're going to see shortly, then that is the load side. Okay. The other thing that we need to know is that in a Y network, it's an abstract concept. I'm not going to go in too much detail. This is not the time and place to discuss that. But in a Y network, you have a neutral that is accessible. Okay, you can actually physically connect to the neutral or bring the neutral out, ground it, or have a low resistance grounding, high resistance grounding, reactor based grounding. Whatever you want to do, you can actually access it. And if I tell you that there is actually a neutral over here in delta as well, okay, you're going to say like, Wasim, I cannot see it. Neither can I. But the fact of the matter is that this neutral, geometrically at least, does exist and it is inaccessible. Okay, we cannot access it. When we discuss single line to ground fault and when we go into details around why the single line to ground fault on an ungrounded system does not result in activation of overcurrent protected devices, and we have to create the phasor diagrams and whatnot, we actually work with a neutral reference, okay, in order to fully understand it. But let's just leave it aside and understand that in a delta network, you don't have an accessible neutral. Okay, so the key takeaway over here for you, if you didn't know this before, and even if you just walk away from this session understanding this concept, that from a conventional standpoint, from a communication standpoint, from an assumption standpoint, whenever you see subscripts which are small letters, it actually indicates the source side. Hopefully just this piece of knowledge would help you become a little bit more competent and confident in dealing with the terminology when it comes to three-phase systems. Now, the opposite is also true, which is that if you have letters which are capital, okay, if we have subscripts, so for example, if this becomes VA, V capital B, V capital C, V capital A, V capital B, V capital C, we are looking at the load side. And I don't have to explicitly tell you that Wasim, VAB is equal to 480 volt, 30 degrees VRMS. Okay. And then the problem statement continues on, and I ask you to calculate something at the end. Now, if you're scratching your head and you're thinking that, what should I do with the line to line voltage? I can see it's a line to line voltage, but here's the kicker. It's not necessarily obvious. Okay. There is a little bit of an element of ambiguity, right? With respect to VAB being line to line or phase voltage, really depends on the configuration. But anyways, leave that aside. But the first assumption where you're potentially dividing or splitting the probability of getting this question right into a 50-50 scenario is whether you interpret this as a source voltage, okay? If the entire circuit is drawn out for you, slam dunk, right? But that is like expecting that you're going to be spoon fed. Highly unlikely, at least for the PE power exam, okay? Or this is a load. Now, if you attended the session, you're like, I do remember Wasim saying something about the subscript, small letter, capital letter. So this is capital letter. So this is actually on the load side, and that will all of a sudden unlock the problem for you. Okay. So power systems, honestly, is very easy when you are able to understand the rules of the game. Unfortunately, the fact remains that a lot of times we don't invest enough effort, okay, especially if you're starting out or if you don't work in a technical capacity to really understand the basics. It's like with any other game, right? If you are not into American football and if you randomly watch American football, you won't be able to appreciate the nuances and the fine details, right? Some sports, some games are pretty intuitive. With soccer, you just have to hit the ball in the goalpost, right? It's kind of intuitive. Um, but the more you understand the nuances and the finer details, the more you get to appreciate the field of knowledge or whatever you're dealing with and enjoy it even. Okay, so this is an example of where the terminology sort of can put you in a spin. Okay, is that clear? Any questions? And when we say that we have a balanced load, simply speaking, it basically means that impedances on each and every one of the phases, whether you're connected in delta, whether you're connected in Y, are equal in magnitude and they have the same makeup. So without going in so much detail, because we have to tackle delta network, an impedance is made up of a real component and an imaginary component. Okay. When I say Z1 is equal to Z2, that basically means the entire makeup, the entire composition of Z1 and Z2 is basically equal, right? Such that the real components are equal and the reactive components are equal. So this is a requirement for a balanced load. If we don't have a balanced load, then the current draw is going to be different, even if the voltage is constant on the source side. And that basically disrupt your three-phase balance system, because all it takes for the system to become unbalanced is your either magnitude on any one of the phases or the phase angles on any one of the phases to be inconsistent. The phase angles have to be 120 degree perfectly apart from each other, and the magnitudes have to be identical for a balanced system. Okay, and then we have a delta-Y configuration, delta and Y impedance transformation, which is very important to understand. All else being equal, this is another key takeaway. It is easiest, okay, if I go back to these possible configurations, it is easiest, highly recommended. I tell my students in my electrical program and power program that don't try to improvise on the day of exam. Just convert the source into a Y configuration if it is not given in Y configuration, and the load into Y configuration if it is not given in Y configuration. In fact, I tell them during my three-phase review that remember this, YY. Okay, that is the name of the game. If the source is not given in Y configuration, you convert it into a Y configuration. There are just a couple of steps. And if the load is not in Y configuration, here's the formula. Convert the delta impedance into Y configuration. You just scale the magnitude scale it down by a factor of 3. That is it. Anything else that you're going to try, you can solve it potentially, right? But it is going to be more problematic than a simple YY conversion. YY conversion is easiest because you're able to reduce it into a simple Ohm's law and easily evaluate it on a per phase basis. For any one of the phases, once you unlock any one of the phases, you just simply adjust by 120 degrees for voltage and current, and you have unlocked the remaining two phases. Clear? Now, what if the load is not balanced? Yes, this applies to a balanced system. If the load is not balanced, then we have to deploy additional set of tools. Okay, for a balanced system, the modus operandus is that you bring the configuration delta Y, Y delta, delta delta into YY. If it's already YY, you don't need to convert anything. Once you have a YY configuration, you're able to apply Ohm's law directly, solve it on a per phase basis. Life is good. If we have an unbalanced system, what we are discussing over here, the tools that we have at our disposal cannot be used directly. There is an advanced concept that we encounter in PE power called symmetrical components. We actually have to resolve the unbalanced system into positive, negative, and zero sequence components. Once we have it resolved in positive, negative, and zero sequence components, then we can actually analyze and go from the sequence components into the phase quantities using matrix transformation. So there are at least 2 to 3 steps that are involved in analyzing the unbalanced systems. Version 2 of an unbalanced system is a fault scenario. So within faults as well, we have balanced faults, which we call symmetrical faults. They are our three-phase faults. They can be L, 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 or L, 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 G. Now, for this category of faults, we call them symmetrical faults. You can actually directly use the same rules that we are using right now because it still remains a balanced system. But then all the unsymmetrical faults, okay, for all the unsymmetrical faults, we have to again use sequence components. Examples of unsymmetrical faults, or I should say that the definition of unsymmetrical faults are basically the faults that are not impacting all the three phases equally. Okay, so single line to ground, double line to ground, line to line, one of the phases being open. So these are all the examples of unsymmetrical faults, and we have to rely on sequence components in order to solve them. Make sense? So I hope that you can see the benefit of having a structured approach, first principle based approach, level 3 understanding, not skipping any steps, going through all the details step by step. And if you just extrapolate this and imagine working through every single concept for the FE electrical and computer exam preparation, as well as a PE power exam preparation in a stepwise manner, and not only just the explanations within my FE electrical and computer exam preparation program, you can find details on my website, studyforfe.com. Every single topic is broken down into conceptual pieces, granular pieces that you can understand, followed up by high quality practice problems with a lot of details, stepwise explanations. You will essentially be in a far better position to take on these exams with confidence. And time is of essence, essentially. You can find details, do your research, free resources, ChatGPT, Google. There is no shortage of information, at least in this current age, right? So you can always find answers to the questions that are bothering you. But the question is, how much of friction and overhead you're going to experience. With my program, it's essentially a one-stop shop with a lot of support structure around it. I have a community, an exclusive community for my students where they can ask any technical questions. I assist them with all the responses. My teaching assistants help them with all the responses. And in a very structured manner, you will always be getting answers to your questions in a very short period of time. And they are computer simulated practice exams. So at the end of the day, if you have enough commitment, enough passion, enough incentive, any journey can be completed, right? A journey which is not laid out properly can potentially look like this. But if you use a structured approach, it can be a little bit more easier and, dare I say, a little bit more fun to go through as well. So feel free to check out my exam preparation resources for both FE electrical and computer exam as well as PE power exam at my website, studyforfe.com. If you want to just do a monthly subscription, the monthly subscription is available. You'll get access to the on-demand course. If you go with the on-demand plus live training bundles, then you will also have weekly live training on top of the on-demand course. And then also master classes, which are essentially crash courses on every single topic. And both FE electrical and PE power programs contain upwards of 1,000 practice problems in the coursework combined with the computer simulated practice exams that mimic exact exam-like conditions in terms of the timer and everything, diagnostics, flagging, going back and forth between the questions, the navigation, and the whole 9 yards. If you're new to this channel, please consider subscribing. On a weekly basis, I'm creating content for FE electrical and PE power exam preparation. I also discuss topics related to electrical engineering with a focus on power systems engineering. If you'd like to learn more about my FE electrical and PE power exam preparation programs, please visit my website, studyforfe.com.